Finally, let's walk through part F. Look at the parents' phenotypes and get what info you can from them. The first parent has dark coat color, so it could be big C, little c, or big C, big C. It has long hair, though, so it must be little s, little s. The second parent must be little c, because it has the recessive albino coat color. It has dominant short hair length, so it could be either big S, little s, or big S, big S. Already, we can see that we'll be dealing with test cross type results here, since we've got parents homozygous recessive for the different genes. Let's go to the progeny numbers for coat color alone, and we see there that there are 17 plus 11, or 38 progeny with the dominant dark coat color phenotype. 23 plus 19, or 42 progeny, have the recessive albino coat. That means we've got a 1-to-1 phenotypic ratio in the progeny for the coat color gene, with one parent being homozygous recessive little c, little c. That means we've got the test cross to a heterozygote situation here again, which means that the other parent must be a heterozygous big C, little c for the coat color gene. For hair length, 17 plus 23 or 40 progeny have dominant short hair, while 21 plus 19 or 40 progeny have recessive long hair. Again, that's a 1-to-1 phenotypic ratio, and the first parent is homozygous recessive for the hair length gene. So we've got the same test cross to a heterozygote scenario yet again, and the second parent must be a big S, little s heterozygote, which gives you your final answer for part F. Part G then takes things up a notch in complexity. It asks you to figure out what the genotypes would be for particular classes of progeny from part F. Then we're to imagine taking two of those progeny guinea pigs and breeding them together as new parents, and then part G wants to know what will the phenotypic ratios be for their offspring. To figure this all out, let's go back to our answer for part F. These are the parents' genotypes we just figured out in part F. What we need to know first for part G is what would the genotypes be for short-haired, dark-coated offspring from part F, and for long-haired, dark-coated progeny from part F. Let's start again with what we know from phenotypes. We know that these progeny from part F will be new parents in part G, and that they will have the dominant dark coat color. That means they could be either big C, little c, or big C for the genotype for the coat color gene. Can we narrow that down any further? Yes, we can, actually. If we look back at the answer for part F, these progeny we're considering at the bottom here came from a cross where only one parent had a big C allele of the dominant coat color gene. The other parent only had little c, little c. Thus, there's no way these guinea pigs could be double big C for their genotype of the coat color gene. At most, they could have gotten one big C dominant allele from one of their parents. That means if they're going to be dark-coated, they must be heterozygotes and must be big C, little c. Next, the lower prospective parent has to be little s for the hair length gene, since they have the recessive long hair phenotype. The upper new parent has short hair, so they could, in theory, be big S, little s, or double big S, but just like a second ago, we know that the upper guinea pig has to be big S, little s heterozygous, since there's no way they could have inherited a big S dominant allele from both parents, as only the right-hand highlighted parent above even has a big S dominant allele to pass on to its offspring. All right, with that heavy lifting out of the way, now we have both of the new prospective guinea pig parents' genotypes. What does part G want then? It asks you to figure out if you were to cross or breed these guinea pigs together with each other, what would be the phenotypes of the progeny they generate, and what ratio would they be in? One tool, the main tool we saw for figuring this out in lecture, is to use a Punnett square, in this case a 4x4 Punnett square. On one side, you put all the possible genotypes for these two genes that a gamete, for example an egg or a sperm, from parent 1 could possibly have. This could be big C, big S, or big C, little s, or little c, big S, or little c, little s. Then do exactly the same thing for parent number 2. The other parent could have gametes with genotypes of either big C little s, or again big C little s, or little c little s, or again little c little s. Once you've labeled the sides of the Punnett square grid, you need to fill it out in each square by combining the genotypes from the matching row and column, like so. Now once you've done that, what will be the phenotypic ratios? To figure this out, make a list of the different phenotypic classes, which we can just paste here at the bottom left from the earlier parts of the problem. Then, go through the table and find how many boxes in the Punnett square will fall into each phenotypic class. Let's start with guinea pig progeny that have both dominant phenotypes, that is, short hair length and dark coat color. That will be every progeny with at least one big C allele and at least one dominant big S allele. We can see that there are actually 6 of them here, so we can mark that down in the bottom left. And next, let's look for progeny that would be long-haired but dark-coated. These will be the entries with at least one dominant big C allele, but only recessive little s alleles. If we count them all up, we can see that there are 6 of those as well, so add 6 in the entry to the bottom left. Next up, look for a short-haired albino guinea pig progeny from this cross, which will have only little c alleles, but must have at least one big s allele. There are 2 of those, marked in green here. Add the 2 down in the right spot in the bottom left table, and then finally we can count up the albino long-haired progeny, which will have all recessive alleles for both genes. There are 2 of those also in our 4x4 Punnett square here, marked in purple. So mark that in the bottom left, and then if we reduce what we found in the bottom left table here by dividing everything by 2, we can see that our expected phenotypic ratio for part G would be 3 short dark progeny to 3 long dark progeny to 1 short albino progeny to 1 long-haired albino progeny. At this point, I'll mention again that there often are more than one way to reason through these sorts of problems, and you can utilize whichever correct method makes the most sense to you. For example, for part G, we could also arrive at the same answer using the probabilities for each separate gene and by using the product rule. For example, if we're crossing guinea pigs with the genotypes in the upper left together, we know for the coat color gene that we're breeding heterozygote to heterozygote. Any guinea pig born from this cross will have a 3/4 chance that it will have a dark coat phenotype, and a 1/4 probability that it will be albino. By contrast, for hair length, we're test crossing big S little s heterozygotes to homozygous little s recessive guinea pigs. The result will be that for each guinea pig born of this cross, there's a 1/2 probability that it will be short-haired and a 1/2 probability that it will be long-haired. We then could apply the product rule to compute the probability of any given offspring falling into each of our 4 phenotypic classes. The probability of progeny born of this cross being short-haired and dark-coated would be the probability of it being short-haired multiplied by the probability of it being dark-coated, or 1/2 multiplied by 3/4, which is 3/8. The probability of progeny born of this cross being long-haired and dark-coated would also be 1/2 multiplied by 3/4, or 3/8. The probability for short-haired albino guinea pigs would only be 1/2 times 1/4 then, or 1/8. And the same is true for the probability of progeny of this cross being long-haired and albino. Comparing these probabilities at the bottom left and converting them all to integers will give you the same 3 to 3 to 1 to 1 answer for expected phenotypic ratios for part G. Okay, and that's it for this tutorial for BIOS E1A. Thanks for sticking with me, and I hope that this helps with an understanding of these sorts of practice problems and others like them concerning Mendelian genetics. If you have additional questions on this problem or other course topics, please do post them to the course online discussion forums or bring them and ask them in person at the weekly discussion sections. And as always, thank you again for listening.